Welcome everybody to this workshop in memory of Ray Hubler. And so the first speaker for today is Carlos Arreche from the University of Texas at Dallas. And he'll be speaking about the Grothendieck topologies for differential algebraic varieties.
Thank you very much to the organizers for organizing this important workshop in memory of a friend, Ray Hubler. It's a difficult thing for me to do, and I'll do my best to keep it together. The work that I'm going to talk about today has been really part of a long-running conversation with Ray, beginning when I was still a graduate student at the Graduate Center, and you'll see here that well, it's been for the better part of the last decade, and that at different times and different settings, different grants funded opportunities for us to continue discussing these topics. So I don't mean to suggest that the NSF is disinterested in the work so much that it's just taking a long time to develop. The work is also still not quite done, and so if any of you has the technical expertise and interest to help me finish this, please get in touch, and I would love to talk to you more about it. My subject is technical, so I'm going to try to speak about it as plainly as I am able to. So there will be less equations and diagrams and more like sentences. It's a little weird, but I hope that it's okay with you. So I want to begin with putting this work in historical context. People have been studying algebraic varieties for a long time, and these are just spaces that are locally defined by polynomial equations. And for many reasons, people care to understand solutions of polynomial systems. And one way to do that is to think of those solutions as forming a space that you can kind of do geometry with. And the language of schemes is highly technical because it needs to be. Varieties are weird. And in that language, you can bring in a lot of different classical subjects to help you along in studying these objects. Beginning in its most modern form in the 50s with the work of Arreche, followed by Colchin, differential algebra was developed as an analog of commutative algebra, where now you're hoping to be able to understand algebraically solution sets of polynomial differential equations, which also show up classically in many settings. And the hope was that you could emulate the things that people have been doing in commutative algebra to now also better understand differential equations from an algebraic point of view. In particular, one of the successes of this approach was Colchin's spectacular, celebrated Picard-Vessiot theory that places earlier work of Picard and Vessiot on linear differential systems on a firm, modern footing. The quotations around the word modern here are just meant to kind of emphasize that, it was modern at the time, and what happens with using the word modern is that if you wait long enough, the thing stops being modern. If you look at the years, quickly, you'll find that the language of schemes wasn't yet available in its modern form at the time where a lot of these things were developed. In my many years of talking with Ray, he had this vision to try to develop in a differential context technology that would more closely mimic what Grothendieck school was able to do for polynomial equations, but bring it over into the differential world and try to kind of merge the two, both in terms of approach and also in the kinds of results that the Grothendieck school was able to get. Okay, so my main topic in the title is the subject of Grothendieck topologies. Okay, and the definition is technical. So I want to start just talking about what motivates that forthcoming technical definition. You take a topological space X, and you look at the set of open subsets of X. You can think of those open subsets as being the objects in a category. Okay, you've probably heard the word before. If you're not super comfortable with categories, well, this is not the time and place to get into it in detail. But the objects are the open sets, and then the morphisms are exactly the open inclusions. If one open set is not included in the other, there are no morphisms between them. And if they are, then there's exactly one morphism between those objects, being their open inclusion. I'll comment now because it matters later that the intersection of open subsets being open again, that happens to be a fiber product in this category. Okay, whatever fiber product means in category theory, the intersection is what it is in this context. And then this category has a little bit of a funny extra structure. If I give you an open subset of U, I can then isolate collections of other open subsets of U that cover it in the topological sense. Okay, this an open topological cover in that traditional classical definition. And what I'm talking about is familiar. It's not, I think, terribly deep. Let me make some silly observations about how open covers work. Given any subset, you can immediately produce at least one open cover of it, which is itself. I'm calling these isomorphisms because I'm thinking of the future. And then if I give you an open cover of some open subset U, and then for each one of those little open subsets, I give you an open cover of that little guy, then a collection of the open covers of an open cover is also an open cover of the first guy. Okay, so basically here I'm able to refine open covers even further by taking even smaller open subsets. And then finally, if I give you an open cover of some open subset U, and then I give you some other open subset of U, I can intersect the open cover of the big set to get an open cover of the little set. Okay, this is trivial in this context, but later on there's going to be a technical version of this. And if you're nodding along and thinking, why am I wasting time on this? It's because what I'm going to show you later is going to take some work to parse. Don't read it if you haven't seen it before. Just remember that it's meant to be easy. What a Grothendieck topology is, before I give you that technical definition, is somehow an axiomatization of how the category of open subsets of topological space works. Okay, so you're just going to abstract away what is essential about this category of open subsets, together with these little observations about covering families, in order to do sheaf theory. Okay. You've probably heard about sheaves before, and either you've studied them and it's fine, or you haven't, and I'm not going to make it fine now. But let me still say a little word about what they are. A sheaf on a space is a special kind of contravariant functor. Okay, this is just to every open subset, I assign an object, whether it be a set or an abelian group or other things. You can have a sheaf of rings, a sheaf of modules, a sheaf of whatsits. And it's going to be a special kind of contravariant functor. By contravariant, I mean that whatever is assigned to some open subset, if I give you an even smaller open set, I have a map going in the opposite direction, called a restriction map, because I pretend that I'm restricting a thing defined on the big open subset to the smaller one. Okay, and I said it's a special kind of contravariant functor. What makes it special is that you impose conditions on it that make it so that its value on any open set is in some sense required to consist of global objects, global on U, that are locally determined or locally defined. Concretely, I mean the following two things. If I give you two elements of f of U, I can tell whether or not they're equal by restricting them to some arbitrary open cover of that U. Okay, so this is a sense in which the global objects are locally determined. I can tell by just looking inside of small open neighborhoods. The other condition is a little technical. I wrote it out here, but what this is saying in words is that if I give you a collection of things in a small open cover, provided that they agree on intersections, then I'm able to patch them into a global object defined on all of you. This is what makes a sheaf be a sheaf. And there are good reasons to look at them. I'll give you a concrete example of a few sheaves shortly. But for now, let me point out something, an immediate problem that you run into when looking at sheaves is that there's a notion of morphism of sheaves. It's a natural transformation of functors, whatever. If the sheaves consist of abelian groups or sets, I just mean a map of the corresponding sets on each open U. And one can define what it means for a morphism of sheaves to be injective or surjective, and the definition is of a local character. Okay, to be injective or surjective means that you are that thing locally only. Injective and surjective here behave a little differently from each other. One can show using the what makes a sheaf be a sheaf that to be injective in this technical sense actually coincides with the naive version that you would think of being injective. Okay, being injective means that you're literally injected everywhere you care to look. However, it's possible for phi to be surjective in the category of sheaves, and yet for it to fail to be globally surjective on every single open subset U that you care to look at. And sheaf cohomology, what it's for is, in a sense that I'll kind of make precise later, sheaf cohomology is there to measure the failure of being surjective locally, implying that you are surjective globally. You're not always, but to what extent does that fail? Cohomology captures that in a precise sense. Here's a concrete example of a sheaf that led to the abstraction that I just discussed. I give you a topology space, and then for every open, you can take the assignment to that open to be functions, say nice functions, whatever, from that open to somewhere else. Okay, functions are the first example of a global object that's locally determined. Two functions are the same exactly when they give you the same value at every point, right? A super concrete example of this is take for my space to be the puncture complex plane, and then my sheaf is going to assign to every open subset of the puncture plane the set of holomorphic functions from that open subset well, into C. Okay, just a set of holomorphic functions on it. That's a sheaf because functions have this local character. Then here's an exact sequence of sheaves. Okay, this C underlined, that's what it's called in the literature. It really just denotes the constant functions on an open. This isn't exactly just C itself. If the open subset is not connected, then I get to decree one value on each one of the connected components, whatever. Constant functions included in the holomorphic ones, and then I have a map from holomorphic functions back into themselves by just differentiating. The experts will recognize this as a really naive version of the Durham complex. I felt that it was too early to state it in that way. I'm just differentiating from the holomorphic functions back into themselves. And why is this exact? Well, if I give you a holomorphic function, in here, locally, I can always integrate it if I take a really tiny open subset everywhere. But a holomorphic function might not be globally integrable. In fact, the example is very familiar. The function 1 over z is holomorphic on the puncture plane, and from calculus 1 that the logarithm serves as a really reasonable antiderivative for 1 over z. So this is an element of the global sections of this sheaf, and locally I can restrict to some small fine enough open cover of X, and I get to notice that it's the image of some other holomorphic function on that little open set. What I cannot find globally defined antiderivative for this thing. Okay, so here you have a locally exact thing that fails to be globally exact. A fun fact that'll come up later is that even though the logarithm is not a globally defined holomorphic function on all of X, it is an honest holomorphic function on some other surface that you can create from the puncture plane. And it's a beautiful picture. If you've seen it, it's this like infinite helix that you obtain by trying to force the logarithm to be single valued, and so it's an open cover in the topological stack of pancakes sense of infinite degree over the base being the puncture plane. Okay. So it's not globally defined on X, but it's locally defined in at least two different ways. In fact, this kind of one's tempted to try to pretend that the Riemann surface of the logarithm should be a strange kind of open subset of X as well. Okay, and the desire to do this kind of thing is what motivated historically the abstract definition of Grothendieck topologies. Here's that abstract definition that I promised you. I give you a category. I need it to have fiber products, whatever that means. It's something that behaves like intersections of opens, and a Grothendieck topology on that category is for each object. I need to tell you what it means for a bunch of objects mapping to you to constitute an open cover of that U. Okay, here are the axioms. They're difficult to see all at once on the page. If you haven't seen it before, please squint and stand really far away if you must. But this generalizes to this abstract setting the nice obvious facts that we know about open covers of open subsets. And then just a little bit of terminology that I'm going to keep using. A category together with this extra structure of a Grothendieck topology is called a site. A site is like a make-believe space that doesn't maybe exist properly as a space, but I know what the open subsets of that make-believe space are, and they behave in the right way with respect to coverings. Now that I have open covers, I can define sheaves in the same way as before. Okay, they're going to be special kinds of contravariant functors from this category of opens into someplace else. And I'm going to want, in order for such a contravariant functor to be a sheaf, it should satisfy the same sheaf axioms that I wrote down before, except with respect to this new notion of what it means to be an open cover. Okay, I'm not going to write it again. The definition carries through so long as your category has this extra structure satisfying the axioms. Historically, the first example of an exotic Grothendieck topology on a category came out like this. I give you an algebraic variety X, and then there's this notion of a scheme that's étale over X. This is not the time and place to delve into the formal definition, but what you should think of étale things as being are finite covering maps in the topological sense. Okay, that local stack of pancakes definition. And what happens is that if you study such things enough, you realize that they satisfy all of these axioms for being a Grothendieck topology. They just do. One checks and they do. So now there's certainly a new notion of sheaf on a variety, but sheaf with respect to the étale topology. Okay, and it's a productive, and people got amazing results about varieties from studying this topology and what sheaves behaved like. What happens is that there are some naturally occurring sheaves associated to a variety that are related to each other already for like the really big Zariski open sets. And then even though the sheaves are related to each other, some map fails to be surjective already in the Zariski topology. But then if you look at the étale topology, the thing becomes surjective in there, and there are some functorial properties of the cohomology of sheaves that let you do some mathematics. Okay. Let me tell you a little bit more about this cohomology, what it does, what it's for. The abstract definition of a site, together with that technical notion of what a sheaf on a site is, people have some technology available that immediately leads to a notion of cohomology. What happens is that the category of sheaves on a site has enough injective objects, and that makes it so that every sheaf has a thing called an injective resolution, not one but many possible ones. And yet, if you look at the homology of the complex coordinate sections of that injective resolution, whatever that is, you get some groups, actual honest groups. And if you had taken some other injective resolution, you end up getting the same groups. So the cohomology groups are well defined for a sheaf on a site. This is hilarious. Because it's been defined in this way, the cohomology groups have, they automatically have nice functorial properties. If you've heard the word cohomology before, you might have seen this so-called long exact sequence of cohomology. This is one of thousands of consequences of defining cohomology that satisfies the right axioms. So these groups measure important things about the variety, and well, great. So these things exist. How do I go out and find them? And the definition of what they are is not going to help you at all. It's a bit annoying, but they are the right objects. You just don't know how to find them. For that, there's an app too. People who studied these things in the Etal topology first, and now there's a whole industry of people proving results about these things. There's a standard playbook where you do the right moves, turn the right cranks, and outcome actually explicitly computed cohomology groups in certain cases, provided that you understand well enough what it means to go even more local in this site. Okay, I won't tell you how. Just that there's already a guidebook for what to do. Now, Hubler's proposed project that we've been discussing for years had to do with trying to do something similar, but for differential algebraic varieties. And we should talk for a second about what one means by that. For a variety, we already talked about this. Informally, you mean, okay, it's a space, and locally it looks like the solutions of some polynomial system. Formally, in the language of schemes, words, many technical words in some order is what people really mean when they need to prove theorems about them. In the differential world, well, informally, the definition should be similar. It should be a space that's locally defined by differential equations. And what should be formally? Yikes. Well, there have been many proposals over the years, and I can't discuss them all. But one problem is that already not everyone agrees on what a differential ring should be. Okay, we're all here familiar with a delta ring. When I talk about a differential ring, I mean a ring endowed with finitely many pairwise commuting derivations. And this definition is great. There is absolutely nothing wrong with it if you want to study rings. It doesn't globalize very well, though, in my opinion, and this is really just an opinion. Here's the smallest example where things go a little funny. Look at the projective line over a field. Okay, so this has two affine charts that both look like the affine line, and they're glued together in the middle. On each one of these affine lines, that is a spec of the polynomial ring. Okay, and here are two variables, but this is just notation. The y ought to be thought of as the local coordinate centered at infinity. That's the x inverse centered at 0. If you want to make k of x into a differential ring, the first choice that you make is dx. Yeah. And what happens is that if you look at what's happening near infinity on the other affine chart, this is a really strange choice of derivation on what's also a polynomial ring. Okay, so there's nothing wrong with the definition, but if you start looking at projective varieties or more global objects, some charts look beautiful and some charts just look strange. Okay, for this purpose, we decided to adopt a more relaxed notion of what a differential ring. And the notion is technical. Okay, so here's the definition. If you're still following at home, instead of giving you a pre-chosen set of commuting derivations, I'll endow R with an R module that's meant to behave like the differentials, together with a derivation from R into that module of differentials, satisfying some other technical conditions. Okay. Morally, I want to think of this omega R as being the R dual of the R span of the deltas that you want to pretend that we're talking about throughout. What's nice about this definition is that because I haven't made choices ahead of time, it immediately Sheafifies to give you a definition of what a differential scheme is, because of the way that works. One consequence of this more relaxed definition is that if I give you a smooth affine algebraic variety, that is already canonically a differential scheme in this sense, making no choices. It just has a differential structure on it. So that's nice if you want to do differential algebra to study classical, at least smooth varieties. Here's another funny example. Here's my ring R, K adjoint X and X inverse. That's a coordinate ring on the punctured affine line over K. Yeah, like I think of the punctured complex plane that we talked about before. And here I've defined an exotic differential structure on that ring following this definition. And I just built it by hand. Never mind how it's defined. The point is that the variety associated to this, the differential variety, ought to be thought of as some differential algebraic version of this Riemann surface for the logarithm that I didn't have access to before in a purely algebraic context. Now, if you allow differential schemes, suddenly you also, in some sense, have access to this infinite covering spaces for things. We started a little bit late, so I'm not sure exactly how much time I have. Let me know when you know.
Yeah, so we're running a little late. So if you could somehow get to the main point, saying in 2 or 3 minutes, that would be good.
Right on. Here I talk about definite modules and algebras, and these are things that are basically built out of finitely generated differential modules. Okay, so in this language, there's a notion of a differential equation that's captured by this, and a definite algebra is something that looks like it's kind of part of a Picard-Vessiot ring, but maybe not the whole thing. Okay, these are the differential analogs of finite separable extensions of a field. Out of them, you can build a Grothendieck topology on differential schemes. And what's nice about it is that well, in this class of differential rings, Andre developed a version of Picard-Vessiot theory that works not just for fields but also for rings. And what's nice about that is that if you look at the Étale topology that's come up a couple of times, that serves as some kind of geometric version of Gala theory for spaces. And the way that we've defined the Picard-Vessiot side ends up working as a Picard-Vessiot theory for spaces, with many strong analogies that you can read on the posted slides later, because I don't have time to go over them. But there are many strong suggestive analogies. And the things that we've actually proved with them, I'm not going to, I was never going to write down the full definition of what the Picard-Vessiot side is. With Hubler over the years, we proved a couple of things. The first 3 results here say that that the Picard-Vessiot topology gives you the correct cohomology groups where some other topology already gave them to you. So the first 3 results say that it's not wrong. The last one says that there's something new that you get there, at least in low degrees, that you couldn't get before at all. So that's the end of the content. I'm sorry that I got a bit rushed, and thank you very much.
Hey, so thank you, Carlos, for this very nice talk. So let's give him a round of applause. Okay, are there any quick questions, comments? Okay, so let me just ask quickly. Did you ever think about the difference case?
Yes. Well, sorry. Yes, but not a lot. Andre's notion of differential ring is much more general than what I wrote down. He's able to encode a different structure, also using this kind of language, but the omega in that case becomes a non-commutative bimodule, and the comparison between the two is what captures the sigmas in there. And in that context, he's able to develop a difference theory for rings that ought to also globalize really well, in a Sheafy way to schemes. So I'd be curious to see how much one can go in that direction.
Okay. All right. So thank you, Carlos.